A cosmic darkness comes after the last starlight goes out. That's the start of a new chapter, an era ruled by black holes, the most mysterious things in the cosmos. By the end, you'll understand the ultimate fate of all matter and the staggering timeline of the universe's distant future. We'll explore how black holes become the last rulers of a frozen void, and what strange quantum resurrections might happen near the very end of time, what it means for our universe to have a final story. The life and death of stars, that's what drives everything we see. Every star up there is temporary. It burns through its fuel with this fierce, beautiful urgency. On our timescale, it feels eternal, but really it's just a moment. A star is always fighting. Gravity wants to crush it inward, and the pressure from fusion in its core pushes outward. That balance holds for billions of years. But the fuel doesn't last forever. How a star dies, what it leaves behind, that all comes down to how much mass it began with. Our Sun, a pretty average star, will one day use up the hydrogen in its core. It'll swell into a red giant. Its outer layers will drift off into space, forming a planetary nebula, and what's left is just the hot, dense core, a white dwarf about the size of Earth, just a fading ember. It's a quiet end. For stars much bigger than our Sun, the end is different. When their fuel runs out, gravity wins, and it wins fast. The core collapses in a fraction of a second, then rebounds. That rebound is a supernova. For a little while, that one dying star can outshine its whole galaxy. What's left behind is a neutron star, this incredibly dense sphere the size of a city. Or if the core was even more massive, the collapse doesn't stop. It goes right through and you get a black hole. These deaths aren't for nothing, though. They recycle everything. The furnaces inside supernova create the heavy elements carbon, oxygen, iron, gold. They scatter those elements across the galaxy. That material becomes new stars, rocky planets, life. But with every generation of stars, some usable fuel gets locked away. It ends up trapped in white dwarfs, neutron stars, black holes. The universe is slowly winding down. Each star that dies brings us closer to a time when no new stars will light up. The cycle will stop, and that's the prelude. The last star goes out, and then it's just black holes for a long, long time. 100 trillion years from now, the lights go out. That's not a guess. It's a forecast written into the laws of physics. We're in what they call the stelliferous era. The age of stars, it's the universe's springtime, but every spring ends. The universe's calendar is so vast. Our whole history, from the Big Bang until now, is just the first moment of dawn. What comes next is a long twilight, the black hole era. That epoch starts when the last star dies. A dim red dwarf, burning for trillions of years, finally sputters out. And from that point, for a span of time that makes a trillion years seem short, the cosmos is ruled by darkness. The only significant sources of gravity, the only landmarks, will be black holes. This timeline challenges everything. To speak of 100 trillion years is to use a number with no anchor. All of recorded history fits into that span, not as a blink, but as a single atom in an ocean. That scale isn't meant to frighten. It reorients. It shows the universe isn't a static stage. It's a story with distinct, long chapters. The era of black holes isn't a sudden catastrophe. It's the inevitable next phase, and in that profound darkness, a new form of drama is just beginning. The first rulers of the Dark Age are already here. They're waiting, stellar mass black holes, the silent remains of giant stars. They'll be the most common thing in the future. Each one is a monument to a violent end. A star that collapsed under its own weight. Their masses vary, a few times heavier than our Sun or several dozen times. Right now they're hidden inside the glow of galaxies. But when the last stars fade, they'll be revealed. the sole landmarks in an ocean of nothing. So picture the scene. The galaxy was a swirling pinwheel of light. Now it's a vast, diffuse cloud, cold, dead remnants, brown dwarfs, white dwarfs, neutron stars, planets, all drifting in the freezing dark, and moving through this graveyard are the stellar black holes. They're utterly isolated. The distances between them are so vast, light from one would take centuries to reach another. There are no stellar nurseries. No brilliant clusters, just these solitary titans, orbiting the galactic center in an endless, silent procession. But calling them inert would be a mistake. A black hole's influence is its gravity, and that force remains active long after its birth. It will keep pulling on the sparse matter around it. Over eons, a black hole might gather a thin halo. The coldest gas, or it might capture a wandering, frozen planet. But these events will be rare, like a single raindrop falling in a desert once every million years. Their primary activity will be more subtle and far stranger, because even in total isolation, a black hole is not completely black. This is where Stephen Hawking's idea changes everything. His theory says black holes can slowly leak energy. This process is called Hawking radiation. It comes from quantum fluctuations. At the very edge of the black hole's boundary, its event horizon. It means these dark rulers are, in an incredibly faint way, glowing. The glow isn't light as we know it. It's a whisper of particles escaping the black hole's grip. For a stellar mass black hole, this whisper is so faint. Today it's drowned out by the cosmic background. But in the absolute cold and quiet of the black hole era, this quantum sigh becomes their defining characteristic. It's a process of unimaginable slowness, a slow leak of their very mass and energy back into the universe. Through this faint radiation, they're connected to the cosmos, slowly transforming over timescales that defy comprehension. Their silent dominance is a quiet, persistent decay, a contrast so profound to the explosive, brilliant deaths that created them. Stellar black holes aren't the real kings of the dark. The supermassive ones are. They're the final rulers, anchored at the hearts of dead galaxies. Each one is a cosmic monster. Its mass isn't measured in suns, but in millions of suns, billions of suns. The stellar ones drift in isolation, but these giants are the enduring centers. They're the last structures standing. Everything else has dissolved. A featureless sea of dark matter and dead remnants. Think of a galaxy. It was a brilliant city of stars, all orbiting a central point. An invisible point, that was the supermassive black hole. For billions of years it fed. It ate gas and stars and powered quasars. But in this era, the feast is over. The galaxy has evaporated, its stars have died, or they've been flung out into the intergalactic dark. All that remains is the monarch, alone. The supermassive black hole sits in near-perfect emptiness. But its influence is still immense. Its gravity warps spacetime for light years. It creates a permanent well, an invisible well in the cosmos. The universe is growing uniform and cold. And these dark wells, they might be the only landmarks left, the final anchors for a structure that once held 100 billion stars. Their fate, though, is tied to the same quantum rule. They emit Hawking radiation too, but for a black hole with the mass of 1 billion suns, the process is almost frozen. The evaporation rate is inversely related to mass. The bigger the hole, the colder it is, the slower it glows. For these colossal monarchs, the whisper is so faint, it's nearly silent. It would take a number. A 1 followed by 92 zeros in years, for one to fully evaporate. To even conceptualize that duration is to confront deep time. It makes the current age of the universe seem like a heartbeat. Yet it's not infinite, and that slow, inevitable decay, it points to the final chapter, the strangest chapter of all. That faint glow from a black hole is a slow leak. It's losing itself. That's Hawking radiation. It's a quantum escape act right at the edge of the event horizon. The theory says space is never truly empty. It's a sea of virtual particles popping in and out of existence in pairs. They usually annihilate each other instantly, but if it happens right at the brink, one particle can fall in. The other escapes. To someone watching, it looks like the black hole just emitted a particle, and to do that, it had to pay. The energy for that comes from the black hole's own mass. So very slowly, it loses weight, it evaporates. For a typical stellar black hole, this process is almost glacial. It would take a 1 with 67 zeros after it in years to vanish. That number is so large it has no name. It dwarfs the current age of the universe by an almost laughable degree. In the black hole era, this whisper becomes the dominant sound. The primary source of energy won't be starlight. It will be this faint quantum sigh from dying dark objects. The universe's last significant structures are on a countdown timer. A timer set to timescales that break our intuition. This evaporation introduces a paradox for the so-called heat death. The classic idea was a universe uniformly cold and dark where nothing happens. But with black holes slowly evaporating, the end isn't perfectly silent. It's punctuated by these incredibly rare, incredibly faint emissions. The last flickers of light in all of creation won't come from stars. They'll come from the graves of stars. It's a cosmic irony written into the fabric of reality. The cosmos has this long, quiet middle chapter. Astronomers call it the Degenerate Era. It's not an age of creation, it's a slow fading. All the brilliant furnaces are gone. What's left are the embers, the ashes, white dwarfs, the Earth-sized cores of dead suns. Neutron stars, city-sized balls left by supernova, and drifting among them countless failed stars, brown dwarfs, lonely, frozen planets untethered from their suns. This era lasts for quadrillions of years, a span so long it makes the current age of stars seem brief. The universe isn't fully dark yet. It's illuminated by a dim, residual glow. The leftover heat from stellar lives, like touching a stone that's been sitting in the sun all day. Long after sunset, it still holds a faint warmth. That's the universe in the Degenerate Era. These remnants are cooling, giving off their last stored energy into the expanding dark. It's a light without fire. A memory of light, but even in this twilight there's occasional drama. The dance of gravity never stops. Over these staggering eons, the slow gravitational waltz of these dead objects will sometimes go wrong. Two cold white dwarfs circling each other for billions of years might finally spiral together, collide. That collision could reignite fusion, a brief, spectacular moment. A final phantom supernova in the dark, or it might create a new black hole, adding a fresh monarch to the coming era. These events are incredibly rare. Like a single firefly flashing once in a century in a continent-sized forest, but they're important. They're the last acts of stellar rebirth, the final punctuation marks in the story of star stuff. This long twilight is the essential prelude, the universe slowly exhaling, settling its accounts, preparing the stage for the next, even stranger rulers to claim their dominion in the perfect night. The stage for this dark age is being built by forces we can't see. The universe's evolution isn't just about stars dying. It's shaped by two invisible architects. Dark matter and dark energy. Their influence is quiet, but it's absolute, and they will sculpt the final form of the black hole era. Dark energy is the stranger of the two. It's the name we give to whatever is causing the universe's expansion to speed up. Think of it as a kind of anti-gravity woven into space itself. Right now, its effect is subtle. On human timescales, but over the eons, it becomes the dominant force. As dark energy pushes, it stretches the universe, not just the space between galaxies, but the space itself. It pulls everything apart. In the far future, this expansion will have done something profound. it will have pushed galaxies so far apart that their light can no longer cross the void. Each galaxy, or what's left of it, becomes an isolated island, a lonely island of dead stars and black holes floating in an ever-widening sea of nothing. For a black hole, then, the entire observable universe shrinks to just its own galaxy. There is nothing beyond, no other islands to see. The cosmic horizon closes in. It creates the ultimate isolation. Then there's dark matter. This is the invisible scaffolding, the hidden skeleton that holds galaxies together. We know it's there because of its gravity. Without dark matter's pull, galaxies would fly apart. Stars orbit too fast for the gravity of visible matter alone, so dark matter forms these vast, diffuse halos around galaxies. In the black hole era, as stars die and galaxies evaporate, this dark matter halo will remain, but it too will be stretched, diluted by the relentless expansion driven by dark energy. It will become a faint, ghostly cloud, yet its particles, whatever they are, will still drift through space, and occasionally one will fall into a black hole. That's a haunting thought. Long after the last atom of normal matter is gone, the black holes might still be feeding, ever so slowly, feeding on the ghosts of the cosmos. On particles of dark matter, these two dark components work in a tragic balance. Dark matter tries to hold structures together, dark energy tries to tear them apart. And in the timeline of the universe, dark energy wins. It determines the geometry of the future. It dictates that the final era will be one of profound solitude. The black holes, those last monuments to gravity's victory, will be the sole inhabitants, in a cosmos growing colder, darker, and more empty with every passing eon. Their reign is set on a stage of expanding silence, built by forces we are only beginning to understand. Even in that deep silence, things won't be totally quiet. There's a final kind of music, played not on matter but on space-time itself, gravitational waves, the last ripples moving through the dark. Picture a still pond. You drop a stone and ripples move out in circles. Now the pond is space-time, the fabric of everything, and the stones are the most massive objects there are. When two black holes orbit each other, they don't just move through space, they churn it. Their gravity warps the space-time around them. As they spiral in, locked together, they whip that fabric. Just before they merge, they send out a powerful surge, a ripple moving at light speed. That ripple is a gravitational wave, not light or sound, a wave of pure geometry. Space itself stretching and squeezing. If you were in its path, you'd feel yourself stretched taller, then squeezed sideways again and again as it passed through. The effect is incredibly small, but the event that makes it is incredibly powerful. We've just started to hear this music. Observatories like LIGO and Virgo use lasers in long tunnels to catch these faint tremors. When two black holes merge a billion light-years away, the ripple that gets here is smaller than an atomic nucleus, but we can measure it. Every merger we catch is a preview, a rehearsal for the main signals of the far future. In the black hole era, these events become the main show, the last great spectacles. They'll be very rare. Two stellar black holes drifting in the dark for ages might eventually find each other, a slow gravitational dance. Over billions of years, their orbits decay. They spiral closer and then they collide. In that final instant, they release more energy than all the stars shining at once, but that energy isn't light. It's in these invisible ripples. The merger makes a new, larger black hole, one king consuming another, and the gravitational wave it sends out is its birth cry. A single, powerful chord played into an almost empty hall. In that future, there'll be no telescopes to see it, no antennas to listen, but it happens anyway. The ripple travels out forever, through the expanding void, past the ghosts of dead galaxies. It's the last echo of anything active, a final reminder that even in stillness, gravity's drama goes on. These waves are the death knells of the old order, and the only proof that something somewhere still occurs. They're the universe's last way of saying it isn't asleep yet. In this profound darkness, there's one of physics' greatest mysteries, the black hole information paradox, and in the black hole era, that paradox reaches its final form. To see why it matters, you have to think about what information means. In physics, information isn't just data, it's the complete story of every particle. Its identity, its spin, its energy, and by the rules of quantum mechanics, that story can never be truly erased. It can be scrambled, hidden, transformed. But never destroyed. The universe remembers. Now picture a book falling into a black hole. That book is made of atoms, each with its own quantum story. It crosses the event horizon. From outside, it's gone. The information that made the book seems lost inside. But Stephen Hawking showed black holes aren't permanent. They evaporate through Hawking radiation, and that radiation from his early calculations was purely thermal, random noise like static. It carried no information about what fell in. So when the black hole finally vanishes, what happens to the story of the book? If the information is truly lost, a fundamental law is broken. Quantum mechanics would be violated. That's the paradox. Is information destroyed, or is it somehow preserved? For decades, this was a fierce debate. One side said information is lost, that we'd have to rewrite physics. The other said it must be encoded in the Hawking radiation, scrambled beyond recognition. Most physicists now lean toward that. They think the information does leak out, imprinted on the radiation in incredibly complex ways. The event horizon might be a chaotic firewall of quantum data, not a smooth boundary, but proving this is immensely difficult. We don't have a complete theory that merges gravity and quantum mechanics. We're missing the final piece, a theory of quantum gravity, and this is where the black hole era becomes more than a future timeline. It becomes the ultimate cosmic experiment. A laboratory that runs for timescales no intelligence could ever observe. In that era, every single black hole will eventually evaporate. Each one faces this final test. Does it vanish in a puff of featureless radiation, erasing history? Or does its final flash contain the hidden story of everything it ever consumed? The answer defines reality itself. It tells us whether the universe is ultimately predictable, preserving cause and effect, or whether at its deepest level, history can simply disappear. So those silent monarchs of the dark aren't just fading monuments. They are each a question written in gravity and quantum uncertainty. Their slow evaporation is the universe working through the deepest puzzle of its own existence. And we are here at the very beginning of cosmic time, trying to decipher the answer from the first faint whispers. The information paradox makes us look right into a black hole. What's past the event horizon? Our physics stops working at that point of infinite density, the singularity. But maybe the singularity isn't the end. Some of the boldest theories in physics point to a different ending. A kind of rebirth. They say that in the last moments of a black hole evaporating, quantum gravity might show a hidden core, a cosmic phoenix waiting there in the dark. This comes from ideas like loop quantum gravity. It tries to connect the very large and the very small. In that picture, space-time isn't smooth and continuous. It's made of tiny, indivisible loops, a fabric with a finite, grainy texture, and that texture could act like a safety net. When matter collapses under gravity, it reaches such an extreme density that these quantum loops push back. The collapse doesn't form an infinite point. It stops, it rebounds. What you could get is a Planck star, an object of incredible density, squeezed down to the smallest possible scale in nature, the Planck scale. It would be a fireball of primordial energy trapped inside the event horizon of a dying black hole. From outside, you'd still see a black hole, but inside, the story changes. There's no bottomless pit, there's a bouncing quantum core. Now take that to the end of the black hole era. A stellar black hole, after eons of Hawking radiation, is almost gone. Its event horizon shrinks, it gets smaller and hotter, and according to this theory, there comes a point when the horizon pulls back enough to reveal what was always hidden inside. The Planck star is exposed, and in that instant the trapped energy could be released, not as a slow whisper but as a sudden burst, a final flash in the dark universe. This flash wouldn't be like a supernova, it would be something stranger, a release of energy encoded with the quantum history of everything the black hole ever swallowed. It's a speculative idea, far from proven, but it's breathtaking. It means the silent evaporation we talked about might have a dramatic finale. Each black hole's death could be a miniature rebirth. A quantum resurrection of matter and information given back to the cosmos in one brilliant moment. The timeline for this is almost impossible to grasp. For stellar black holes, that final flash is trillions upon trillions of years away. For supermassive ones, the number is so huge it's hard to write down. But the implication is deep. It means the black hole era might not be a slow fade to black. It could be marked by these rare, spectacular events. The last lights in the universe wouldn't just be faint glows. They could be cosmic fireworks, signaling the release of ancient stories held captive for epochs beyond counting. It adds a layer of deep mystery to the far future. A hint that even in the era of darkness, the universe might still have one last quantum surprise. Protons are not forever. That statement, it carries a lot of weight for the far future. The protons and neutrons in every atom, the building blocks of stars and planets and us, we think they're stable, but over the timescales of the black hole era, that stability might be an illusion. Our grand unified theories, they suggest a possibility. Protons can decay. Their half-life is staggeringly long beyond comprehension, maybe 10 to the 34 years or longer. A number with 34 zeros, a timescale that makes a black hole evaporating seem like a brief moment. If that's true, then the fate of all ordinary matter, baryonic matter, isn't to drift forever. It's to slowly disintegrate, a final erasure. Think about the last monuments from our era, the white dwarfs, those cooling embers, the neutron stars, perfect spheres of nuclear matter. Over these colossal eons, they wouldn't just cool, they'd unravel from the inside. Their protons would transform, break down into lighter particles, pions, positrons, photons. They'd dissolve into a faint, uniform sea of radiation. That changes the landscape. Long before black holes evaporate in any significant way, the universe would be swept clean of these solid remnants. The degenerate era, that long twilight, would have an end. The stage would be left with only two things, the invisible dark matter and the black holes. Every last bit of organized matter, if it wasn't already behind an event horizon, would have faded into background noise that makes black holes something more than rulers. They become the ultimate vaults, the last gravitational tombs. Inside their event horizons, matter is taken out of the game, shielded from the slow decay outside. So the iron from a dead star, the carbon from a lost world, the history of every atom that fell in, it's preserved, locked away from the universal decay. For an epoch that stretches almost to the end of time, these dark monarchs aren't just the dominant objects, they're the sole keepers of the material story. They hold in perfect gravitational custody the last physical memory of everything that was. That landscape of supreme isolation goes against every human instinct. Our minds are built for a world of light and proximity. We measure our lives in years, our journeys in miles, but in the black hole era, those scales stop meaning anything. The distances are so vast they're not just empty, they're actively growing. Dark energy keeps working, stretching the fabric of space itself. The nearest stellar black hole might not be a few light years away. It could be a distance so great that light from it would take longer to arrive than the current age of the universe. To call it nearby is a misunderstanding. It's an island in an ocean that's itself expanding faster than any signal can cross it. Picture standing on a frozen, barren plain at night. You're holding a single, dying match. That flicker is all the light in creation. You look out and there's nothing to see, no horizon, no landmarks, just an infinite black in every direction. That's the visual reality. The cosmic microwave background, the faint afterglow of the Big Bang we see today, will have been stretched by expansion. Its wavelengths pulled so long, its photons so weakened, they fade into undetectability. The universe's first light goes dark, and no new starlight is being made. The only illumination comes from processes so faint they're whispers. The Hawking radiation from a black hole isn't a glow you could see. It's a trickle of particles over timescales longer than nations rise and fall. An occasional flash from a proton decaying inside a long-dead neutron star. Or from two dark remnants colliding after eons of drift. These events are like single sparks flying from a campfire that went out 1 trillion years ago. In that environment, the concepts of here and there, of now and then, they start to unravel. With no constant light sources, no reliable clocks ticking in the sky, how do you measure time? With landmarks receding into invisibility, how do you chart a course? Existence becomes a question of pure persistence, not progress. A black hole simply is. It doesn't evolve in any meaningful way over spans we can comprehend. It's a monument to a past so distant that the event which created it isn't a memory. It's a geological layer in the fossil record of the cosmos. This challenges observation at its core. To observe something, you need information to travel from it to you. But if the space between you and everything else is expanding faster than light can cross it, you're in a prison of solitude. Each black hole becomes its own observable universe. A tiny domain beyond which nothing can ever be known. This is the ultimate stillness, not the quiet of a forest, but the quiet of a finished story. The drama of gravity continues, but its actors are so far apart they'll never meet. The faint quantum processes continue, but their pace is glacial. It's a universe that's settled into its final, deep equilibrium, a state not of death but of a profound and permanent rest. And in that rest, the last sentient thought, the final observation, becomes the most precious and lonely artifact in all of reality. Time becomes a prisoner of gravity. Right at the edge of a black hole, Einstein's ideas about time dilation reach their limit. It's not just a clock slowing down, it's the tempo of reality itself warping. For someone falling into one of these things, their own time would feel normal, their proper time, but looking out, the view would be bizarre. The frozen cosmos outside would seem to speed up. Like someone hit fast forward on the universe. Already dark galaxies would redshift away in a blink. The black hole's own evaporation, a process that takes longer than any number we can write, would play out before their eyes. In a finite span, from that falling perspective, they could see the entire future history of the object eating them. They might see its final quantum flash. Whatever comes after, all before they even cross the threshold, and that bends philosophy. It means the end of time isn't a single moment for everyone. It's relative. It depends on where you are, how you're moving. For the universe, the black hole era lasts epochs beyond counting, for the last bit of matter falling in near the very end. That whole colossal future might be compressed into a fleeting, final observation. Two timelines, both real, unfolding at wildly different rates. One is slow, cold, stretched across a canvas that seems infinite. The other is a rapid, fiery conclusion, seen from the brink. This relativity adds a layer. It means for the black holes themselves, the story could have a very different duration. The slow evaporation we chart from the outside could be, from a certain falling perspective, a brief and brilliant finale. It challenges the idea of a cosmic calendar. There's no master clock ticking to zero. There are only personal histories woven together by gravity and motion, each with its own beginning, middle, and end. So when we say the era of black holes lasts unthinkable spans, we also have to hold the thought. For the entities at the very heart of the story, the end might arrive in a flash. A flash of comprehended eternity. That profound silence from that era, it opens up a strange possibility, a universe that's run down, approaching what's called heat death, a state of perfect equilibrium. In that state, the laws of probability, they start to mean something bizarre. Over an infinite span of time, even the most wildly improbable event isn't just possible. It becomes inevitable, and that leads to one of the most speculative ideas in cosmology, the Boltzmann brain, named for the physicist Ludwig Boltzmann. It's not a biological organ, it's a random, fleeting assembly of particles, a quantum accident in the void, a configuration of matter that, by sheer chance, arranges itself into a conscious, thinking entity. For a single moment before dissolving back into chaos, in the near-perfect uniformity of the far future, the spontaneous formation of a star or a galaxy that's impossibly unlikely. It would be a massive leap away from equilibrium, but a single, disembodied moment of awareness, a phantom thought with no past or future. The mathematics suggests that, given enough time, such a tiny, ordered fluctuation is more probable than the rise of an entire civilization. This pushes the anthropic principle to a breaking point, the idea that the universe must be compatible with observers like us. If Boltzmann brains are possible, and over infinite time they vastly outnumber ordinary, evolved observers, then a startling question emerges. Which kind of observer are you more likely to be? A being with a continuous history, born from billions of years of cosmic evolution, or a momentary flicker of false memory, conjured from the random motions of particles in an eternal dark? The logic suggests you should almost certainly be the latter, a brain that just popped into existence, complete with the illusion of a past, contemplating a universe it never actually experienced. Most physicists find this conclusion deeply unsatisfying, a sign that our understanding is incomplete. It acts as a boundary for our theories. A viable model of the cosmos must make such Boltzmann fluctuations so incredibly improbable that they are effectively impossible. Or else the entire framework of rational inference crumbles. Yet in the context of the black hole era, the idea gains a haunting, poetic weight. Long after the last black hole has evaporated into a faint mist of radiation, in the era of true nothingness that may follow, time stretches forward without end. In that endless quiet, the universe isn't completely dead. It's in a state of maximum entropy, yes, but quantum mechanics tells us there's still a faint hum of activity. Virtual particles still flicker, and over durations that make the black hole era seem brief, those flickers could, by pure chance, assemble into a configuration that thinks. The last observer in all of creation might not be a descendant of stars. It might be a random thought, born from the cold geometry of empty space. A solitary, self-aware question mark that forms, wonders at the infinite dark for an instant, and is gone. It ties the ultimate fate of matter and energy to the deepest mysteries of consciousness itself, suggesting that even in the final stillness, the universe might not be entirely devoid of witness. A civilization that lasts has to be measured against the cosmic calendar. It changes how you think. A species that gets through its own technological adolescence, that spreads out into the stars, will eventually face the universe cooling down. Their science wouldn't be for short-term gains. It would be a long-term engineering project on a scale we can't really conceive. Their monuments wouldn't be pyramids. They'd be the manipulation of fundamental forces across eons. A truly advanced intelligence might see a supermassive black hole not as a threat but as a resource. The last great battery in a dying cosmos. Theorists like Freeman Dyson thought about this. He suggested a civilization could build a structure, a Dyson sphere, but not around a star, around a black hole. To capture its Hawking radiation, that faint quantum whisper could be harvested, converted into usable energy for unthinkably long periods, or maybe they'd use the black hole itself. Its immense gravity, the warped spacetime around it, could serve as an ultimate computer, a computational substrate where information is processed with staggering efficiency. These aren't projects for a millennium, they're blueprints for a quadrillion years, a plan that outlasts galaxies. This perspective redefines legacy. If the final state of everything is a cold, dark uniformity, then what's the point of building anything, of creating art or accumulating knowledge? The answer might be that the meaning isn't in creating a permanent record on a cosmic stage that will go dark. The meaning is in the act of understanding, in the journey of discovery itself. A civilization's ultimate achievement wouldn't be an eternal empire. It would be the comprehension of the universe's story, from its fiery birth to its silent end. Their culture would be one of deep time, their ethics shaped by responsibility across generations they'll never meet. They'd become curators of cosmic history, shepherding the last pockets of complexity against the tide of entropy for as long as physics allows. For us here at the dawn of our own story, this isn't a call to despair. It's a call to perspective. It suggests our struggles, our art, our science. They matter not because they'll echo forever in a static universe. They matter because they are part of the brief, brilliant flowering of complexity, a chance to see and to know. In the face of an inevitable future ruled by darkness, the act of looking up and asking why becomes the most profound rebellion. It's how we, or any civilization, leave a mark not on the cosmos but with it, by bearing witness to its grandeur and its mystery, all the way to the final, quiet page. These future timelines are so vast, they challenge science itself. How do you study eras that will begin long after our sun is gone, after our galaxy, after all life as we know it has faded? The answer is a mix of trust and calculation. You trust the fundamental laws of physics, the rules we've tested in our own brief moment of cosmic time. You take the equations of general relativity which describe gravity and the shape of the cosmos. You use quantum mechanics, the rules of the very small. And you apply thermodynamics, the laws of energy and disorder. Those are the tools. The assumption, a bold one but necessary, is that these laws don't change. That gravity will behave the same way in 100 trillion years as it does now. With that foundation, you can extrapolate, you can run the equations forward. And that's where immense computing power comes in. Supercomputers are tasked with a simulation of almost unimaginable scope. They model the gravitational dance of trillions of dark matter particles. They program in the relentless push of dark energy, causing the simulated space itself to stretch. They seed this digital universe with conditions we observe now, and then they let the simulation fly forward. Watching as galaxies form, collide, and then slowly drift apart into the void. They track the life and death of stars, the slow orbital decay of black holes, the faint glow of Hawking radiation over epochs no human will ever witness. These aren't guesses, they're mathematical narratives built step by logical step. Of course, these models carry uncertainties. We don't yet know the exact nature of dark matter or dark energy. There may be unknown physics, some grand unified theory, that could alter the story in its final chapters. The possibility of proton decay, for instance, rests on theoretical predictions not yet confirmed. But within the framework of our current understanding, these simulations are rigorous. They are our best possible glimpse. They paint a consistent portrait, a haunting one, of a future defined by gradual dissolution. A fading of all structure into a cold, uniform darkness. The awe this inspires isn't just about the scale. It's about the power of the human mind to reach out with mathematics and logic and trace the silhouette of an ending so distant it defies all intuition. Using the light of reason to illuminate a time beyond the reach of any light. But that long, quiet freeze isn't the only way it could end. Everything we've been talking about, that whole dark era, it all depends on one idea. That the universe keeps expanding faster forever. That dark energy is just a fixed force, a constant, but cosmology, it's full of other possibilities. And some of those possibilities, they lead to very different endings. One of them is called the Big Rip. In that case, dark energy isn't constant, it gets stronger. Its repulsive force becomes more and more dominant. First, it just pulls galaxies apart faster, then it tears galaxies apart. Clusters of stars get ripped away. And as the force grows, it doesn't stop with the big structures. It goes after the small ones. Solar systems are pulled apart. Planets are separated from their stars. Eventually, the force gets so strong it overcomes the forces that hold matter together. Stars and planets are torn apart. And finally, in the last instant, it would overcome the forces inside atoms. Molecules, atoms, atomic nuclei, all ripped apart. The fabric of spacetime itself might be shredded. In that timeline, there's no long black hole era. The black holes would be destroyed. Their event horizons would be pulled apart before they could evaporate. The universe would end with a violent, fundamental disintegration. A finite and dramatic end to everything. The other major alternative is a reversal, the Big Crunch. Imagine the expansion of the universe, that initial explosive energy finally slowing down. The collective gravity of all the matter, it acts as a brake. It overcomes the push of dark energy, the expansion stops, and then it reverses. The universe starts to contract. Galaxies, after flying apart for billions of years, start to fall back toward each other. The sky would get hotter and brighter, the light blue-shifted. The cosmos becomes a pressure cooker. Galaxies merge in catastrophic collisions. Space is squeezed. Temperatures rise to levels not seen since the first moments after the Big Bang. All structure is erased, and eventually everything, every particle, every bit of energy is compressed into an unimaginably hot, dense state, a singularity. Maybe triggering a new Big Bang, a new cycle. In that cyclical model, the black hole era gets cut short. It might never even fully begin before the Great Contraction pulls everything back. These aren't just guesses, they're mathematical outcomes from tweaking the parameters in our models. The strength and nature of dark energy, that's the key. Our current best measurements point to a constant dark energy, leading to that eternal expansion, the long freeze. That's why the era of black holes is our most robust forecast. But science is about what the evidence says, and evidence can change. Thinking about these different endings, the rip, the crunch, the freeze, it does something. It frames that immense, silent reign of black holes not as a certainty, but as the most likely path in a story that's still being written. It reminds us that the future of everything depends on forces we're only starting to measure. That the ultimate fate of the cosmos hangs in the balance between two invisible titans, the relentless push of dark energy and the patient, persistent pull of gravity. Gravity's quiet rule creates a different kind of scene, not a sky full of lights, but one defined by deep absences, and that picture of the far future raises a hard question. Can a universe that's mostly darkness and empty space be called beautiful? We usually tie beauty to light, to color, to living things, a sunset, a forest, a galaxy full of young stars. But there's another idea, the sublime, a feeling of awe and terror when you face something much larger than yourself, a stormy ocean, a mountain peak, a desert that doesn't end. The black hole era is the final form of that. Its scale isn't just huge, it's beyond understanding. Its main features aren't things you can see, they're pits in space-time you can only deduce. Its timeline makes everything human, every effort, every empire, every memory shorter than a passing thought. There's a harsh, frightening beauty in that. A beauty of pure geometry and unchanging physical law, unfolding on a stage that's almost nothing. It's the beauty of a solved equation, elegant and cold. That challenges our need for story. We're storytellers. We look for beginnings, middles, ends. We search for purpose in a life, in a civilization's arc. But the cosmic story, as we can guess it, points to a different plot, one where the grand finish isn't a climax. It's a slow fade into quiet, where the main characters aren't creators. They're preservers, and then finally, just fading monuments. It can feel like a story of loss, of pointless fading. And yet, from physics alone, it's not an ending in nothing. It's a change into a state of total balance. The universe isn't dying in the sense of stopping to exist. It's becoming its most likely, most stable form. The drama of making and breaking gives way to the deep quiet of entropy. Our trouble with this idea shows a human bias. We are temporary, bright flashes of order. And we naturally value the conditions that made us. We see the stelliferous era, the age of stars, as the universe's active, interesting chapter. But to the universe itself, that era is just one part. The long eras of darkness that come after are just as much its story. They aren't a mistake, they aren't a tragedy. They're simply what comes next by the rules. That leads to maybe the most humbling thought. It makes right now feel incredibly precious. We exist in the cosmic spring. We're here in the brief time when the universe is lit up, when complex chemistry works, when questions can even be asked. We're living in the one chapter where the cosmos can look at itself and wonder about its own fate. That ability to wonder, to search for meaning even facing an ultimate freeze, might be the most important thing in the whole story. It suggests purpose isn't written into space-time forever. Purpose emerges locally and temporarily in pockets of complexity like ours. It's a story we tell. A meaning we make inside the grand but neutral structure of physical law. The black holes of the future won't think about their existence. They'll just be. Our ability to look ahead, to imagine that vast dark and feel its sublime weight, that's our unique mark on this brief, brilliant page of cosmic time. This is a final boundary for knowledge. We can map the future with our equations, but we will never see it. The black hole era is a prophecy from physics, a story about a time that lies beyond any observer. The sheer duration is the first wall. A civilization might last billions of years. That feels like immortality to us. But against the timeline of a supermassive black hole evaporating, that civilization's entire history is less than the first tick of a cosmic clock. To witness even a fraction of that progression would require an observer to persist for timescales that physics itself may render impossible. Structures decay. Information degrades. The very protons that make up matter may not last long enough. The universe's future is a show that plays to an empty house. Then there's the problem of isolation enforced by the cosmos. Dark energy doesn't just create distance, it creates horizons. As space expands and accelerates, distant galaxies are carried away faster than light can bridge the gap. Their light, already on its way to us, will one day be the last we ever see from them. Then, even that final photon will arrive, and after that, nothing. The observable universe, the sphere from which information can ever reach us, will shrink. It will contract down to the local group of galaxies, then down to our own Milky Way's remnants. And eventually, perhaps, down to the immediate vicinity of a single, dying black hole. For any entity in that far future, the broader cosmological context, the grand story of expansion and structure we tell today will be utterly lost. There will be no background radiation to measure, no distant quasars to use as reference points. The universe will appear static and eternal and profoundly local. That means the ultimate fate of the cosmos is, in a real sense, a prediction we can never verify. It exists in the realm of logical deduction, not empirical confirmation. We take the laws we've tested in our tiny sliver of space and time, and we extend them forward with mathematics. We have high confidence in those laws. But we cannot be certain they hold unchanged across durations that dwarf our entire experience. This places the era of black holes in a unique category. It's not like predicting an eclipse next year or even the sun's death in 5 billion years. Those are events within a continuous, observable timeline. This is different. This is predicting the state of a reality that will have become, from any practical perspective, a different universe entirely. One where the very tools of observation, light, structure, change have faded into near nothingness. So why do we even contemplate it? If we can never see it, does it matter? The answer is in the power and the limits of science. This exercise shows us the farthest reach of our current understanding. It maps the coastline of the known, and in doing so, it reveals the shore of the unknown. The fact that our theories produce such a stark, specific, and untestable prediction is not a failure. It's a challenge. It highlights the questions we still cannot answer. What is the true nature of dark energy? Is it truly constant, or could it change? Leading to a big rip or a big crunch instead of this long freeze. Does information truly escape a black hole, or is it lost? These are mysteries we can investigate now in our era of light. By chasing them, we are indirectly probing the architecture of that distant dark age. The black hole era stands as the ultimate thought experiment. It's a mirror held up to our scientific ambitions. It shows both how far we can see with the mind's eye and the absolute horizon beyond which direct sight will always be impossible. It teaches a humble lesson. There may be chapters of the cosmic story that are, by their very nature, written to be read only in theory, never witnessed in fact, and in accepting that, we come to value all the more deeply the singular, brilliant chapter we are living in right now. The one brief epoch where the universe is lit, alive with questions and generous with its answers. Gravity doesn't stop, even in that emptiness. The black holes, they're still there, and they'll still feed. The universe isn't a perfect vacuum. Over these enormous timescales, gravity pulls in whatever's left, a stray proton, some cold hydrogen, maybe dark matter. It's a trickle, but it adds up over eons. It spirals in. But it doesn't fall straight down. Angular momentum forces it into an orbit. It forms an accretion disk. But it's not like the bright disks we see now. This is a ghost of that, made from the last scraps, almost invisible. The particles in that disk, they rub together. That friction makes heat. Heat makes radiation. So when that last bit of matter finally crosses the horizon, there could be a flicker. A final, dim burst of light or X-rays. The last real photon, not from Hawking radiation, like a final heartbeat, faint, irregular. These events would be incredibly rare, millennia apart, like a single grain of sand falling in a silent cathedral once a century. But they're significant. They're the last gasp of the old mechanics, gravity turning mass into light. Studying this extreme low-density accretion, it's a frontier. It shows us the absolute limits. When there's almost nothing left to burn, how does gravity still make something happen? The answer is in this slow, grinding process. It means even in the darkness, the universe isn't static. It's still processing, still transforming the last usable material. Each black hole becomes a slow-motion factory, taking the final dust and converting it agonizingly slowly into a faint signal and then into more mass for itself, a cosmic digestion that lasts for eons. So the black holes are still growing, imperceptibly, even as they evaporate. They're decaying and being replenished at the same time, a race across deep time. A delicate balance, the last act of consumption before the final silence. The timeline isn't just large, it's structured. there's a strict hierarchy to how things dissolve based on mass. A cosmic pecking order: the smaller the black hole, the faster it evaporates. That simple rule carves the whole era into layers, each one longer and quieter than the last. It's like a mountain eroding. The small rocks and pebbles wash away first. That takes a long time to us. Then, over much longer stretches, the larger boulders crumble. You're left with the bare bedrock that stands for eons more. The universe does that. The same patient, relentless process. Take a black hole with the mass of a small asteroid. If one could form, it would be incredibly hot. It would evaporate in a burst of radiation within the current age of the universe. We might even see that today. A flash of gamma rays, but that's the extreme end, the tiny end. A stellar black hole with the mass of our Sun sits in the middle. Its evaporation time is around 10 to the 67 years. A 1 with 67 zeros. To write that number out would take more paper than exists on Earth. It already dwarfs every human idea of duration. Then you get to the true monarchs. The supermassive black holes in dead galaxies, one with the mass of 1 billion suns. Its evaporation time enters a realm where our words for numbers fail. It's measured in googolls of years. A googol is 10 to the 100th power. That number is so vast, there aren't enough particles in the observable universe to write it down. Not even if you used every atom as a digit. So the era of black holes isn't one uniform period of darkness. It's a sequence of deepening silences. First, the smaller stellar black holes. They rule for what seems an eternity. Then they finally whisper away into nothing. Their final quantum flashes, rare as they are, become the last punctuating events. For a long, long time, after they're gone, the universe enters a new phase. A phase where the only remaining structures are the supermassive black holes. Each one sits in near total isolation, separated by voids that expansion has made unthinkably vast. They'll keep each other company, gravitationally, for a duration that makes the entire previous black hole era seem like a brief prologue. The time when stellar black holes still existed. It becomes a brief, bustling prologue. This is an era within an era, a deepening of the quiet so profound it redefines the word patient. The universe, in its old age, spends almost all of its remaining active lifetime in this final state. Solitary, massive darkness. This layered dissolution stretches the idea of a cosmic chapter to its limit. It forces you to confront a future not of a single ending, but of endings within endings, each one more remote and more still than the last. There's something hidden in space itself, a kind of wild card. Everything we predict about the far future, black holes evaporating, the final freeze, it all assumes one thing: that the laws of physics are fixed, that the constants don't change. But some of our deepest theories, from quantum field theory, they suggest maybe that's not guaranteed. They say our universe might be in what's called a false vacuum. You can picture it like a ball sitting in a small dip on the side of a hill. It seems stable for now, but the truly stable state, the true vacuum, is way down at the bottom of the valley. The ball is just in a local minimum, a temporary spot. And our whole cosmos, with all its specific laws and forces, could be in that dip. If, through quantum tunneling, pure random chance, that ball somehow got out of the dip, it would fall. That event is vacuum decay. It would start at one random point. A bubble of true vacuum would form, and inside that bubble, the laws of physics are completely different. The fundamental forces, what particles exist, even the nature of space and time, all of it rewritten. And this bubble expands in every direction at the speed of light. Nothing outruns it. From inside our universe, the change is instant, total. One moment, the universe as we know it, the next, something entirely alien. The wall of that bubble is a boundary, annihilation for all structure, stars, planets, black holes. they cease to exist in any form we'd recognize as the new physics takes over. This isn't an explosion, it's a rewrite of reality's source code. The timing is what's chilling because it's a quantum event driven by probability. It could happen at any moment, the next second, 1,000,000,000,000 years from now, or in the middle of the black hole era. Our whole timeline of gradual decay and evaporation could be cut short. Instantly, without warning, by one quantum fluctuation in the void. This possibility doesn't erase our other forecasts, it frames them. It reminds us we're charting the most likely path. Assuming the laws stay stable, but over the infinite stretches of the cosmic future, even the most improbable events, they become possible. Vacuum decay is the ultimate reminder of cosmic humility. It shows that any story about the universe's fate needs a footnote, an acknowledgement that profound mysteries still sit at the heart of quantum reality. Our story of darkness and silent monarchs is powerful, but it's written on a page that could, at any moment, be replaced. The classic heat-death picture is a universe at a uniform temperature. Perfectly still, no energy differences left. That's maximum entropy, where nothing ever happens again. But the black hole era complicates that. It delays that perfect equilibrium for an almost unimaginable length of time, because as long as black holes exist, the universe isn't at a uniform temperature. Stephen Hawking showed they aren't completely black. They have a temperature determined by their mass. A larger black hole is colder. A stellar one might be a fraction of a degree above absolute zero. The supermassive ones are far, far colder. And the space between them, the cosmic void, is even colder. It's approaching the temperature of the background radiation, which itself is cooling toward absolute zero. So you have a situation, these dark objects, each with a faint, specific temperature, sitting in a sea that's even colder. That creates a temperature difference. However minuscule, in thermodynamics, a difference is potential. It's a gradient. It means the universe isn't in perfect equilibrium. Energy can still, in theory, flow from the slightly warmer object to the colder space. That flow is the Hawking radiation itself. That faint whisper is a heat engine, running on the tiniest imaginable temperature difference. It's the last work being done. So the traditional heat death, that state of perfect balance, can't be achieved until the last temperature difference is gone. And that means waiting. Waiting for the last black hole to evaporate completely. For a stellar black hole, that's an astronomical timescale. For a supermassive one, it's a number so large it defies language. This pushes the true end, the moment of final thermodynamic silence, into a future so distant it makes the black hole era seem like a middle chapter. The cosmos doesn't just fade into a static freeze. It engages in a slow, meticulous process, settling its accounts. Each black hole is a last holdout against uniformity. A final pocket of subtle difference, slowly radiating away its uniqueness into the cold dark. Their long reign isn't just a period of darkness. It's the universe's prolonged and patient journey toward its ultimate state of rest. That slow evaporation isn't the only possibility. There are other ideas, some of the most speculative ones in cosmology. They turn the whole concept inside out. They say a black hole isn't a dead end. It could be a gateway, a new beginning. If certain theories are right, that crushing singularity at the center might not be a point of destruction. It might be a bridge to another reality, a separate universe with its own space, its own time, its own laws. Think of it as a cosmic seed. In our universe, a massive star dies, it collapses, it forms a black hole. But what if that collapse doesn't stop at a singular point? In a realm where gravity and quantum mechanics merge, it could pinch off. It could create a new bubble of spacetime, a self-contained bubble, a baby universe. It would be sealed off from our own completely. No information could come back up. No light, but from inside that new realm, its birth might look like a big bang, an explosive beginning from something unimaginably dense and hot. This idea comes from the edges of our theories. From the holographic principle, which suggests all the information about a three-dimensional volume can be encoded on its two-dimensional boundary, so the event horizon could be that boundary. It could hold the data for a whole new cosmos, or it comes from models of quantum gravity, where extreme warping creates a new, disconnected geometry. In the context of the black hole era, this changes everything. It changes the meaning of that long dark age. It would mean every single stellar black hole drifting in the void isn't a tomb. It's a womb. Each supermassive black hole at the heart of a dead galaxy isn't a final monarch. It's a cosmic parent. The death of stars in our universe becomes the creative act that spawns new realities. Our cosmos, in its old age and silence, becomes a nursery for an infinite multiverse. The timeline gets a new rhythm. As our universe expands and cools as stars fade, the process of creating these new realms accelerates. Every gravitational collapse of a massive remnant, every rare collision in the dark that forms a new black hole, each one could be punctuated by the birth of a whole new cosmic story. Our era of darkness would be, from a multiversal perspective, an era of immense fertility, silent fertility. This is, of course, highly speculative. It sits at the frontier. Far from any possible proof, we can't peer into a black hole to see if a new universe is unfolding. The event horizon prevents any information from escaping to tell us. It exists as a possibility, a beautiful, mind-bending possibility, a hypothesis that offers a powerful counter-narrative to eternal freeze and emptiness. It provides a different kind of poetry, one where endings are always also beginnings, where the ultimate fate of matter isn't dissolution into a cold haze, but transformation into new worlds. It suggests the universe might have a deeper, cyclical creativity written into its most extreme phenomena, that even in what looks like a final act of gravitational dominance, there could be a hidden legacy. A legacy of cosmic rebirth. This idea doesn't erase the stark physics of evaporation and decay, but it layers it with a breathtaking potential. It asks us to consider that the true story of the cosmos might be one of endless becoming. Hidden within the heart of darkness, the last supermassive black hole evaporates, and its final quantum pulse, that's the last significant event. With that faint flash, the universe crosses a threshold. It enters its final, simplest state, the era of photons, sometimes called the dark era. This is the ultimate quiet. The long reign of gravity is over. What's left is a sea of the most basic particles, photons, neutrinos, electrons, positrons, all stretched to near zero energy by the expansion. Every proton, every last bit of atomic matter has likely decayed. There are no atoms, no molecules, no solid things. The universe is a uniform cold mist, a fog of the lowest energy light and particles imaginable. This is the heat death. Not as a dramatic end, but as a final, perfect equilibrium, a state of maximum entropy, where no energy differences exist anywhere. Nothing can ever happen again. The cosmos becomes flat in every sense, no hills of gravity, no wells of space-time, just an endless, featureless plane. It is the ultimate stillness. A stillness so complete it redefines the word. This era makes the black hole era seem bustling by comparison. That was a time of structure, of landmarks, of slow change. This is the era after structure, after landmarks, after change. It is the universe's final form, a form of profound and eternal rest. Permanence is an illusion. It's an idea written in human time. Our monuments, our histories recorded across millennia, they feel eternal. They feel that way against the brief flicker of a single life. But the cosmic calendar shows something else. It shows that everything has a lifespan. Mountains erode, continents drift, stars ignite, and then they fade. And this principle, it extends. It goes all the way to the pillars of reality. Those supermassive black holes, the ones destined to rule for gugos of years, they're transient too. They're not eternal monarchs, they're long-lived guests in a universe that is fundamentally in motion. Their evaporation, that final quiet event, it's a testament. A testament to a cosmos where change is the only constant. That shifts perspective. We often look to the heavens for permanence. We want something that lasts forever, something to anchor our fleeting existence. But the universe doesn't offer anchors. It offers a story with distinct chapters. There's the violent, creative fury of the first moments, the brilliant, star-filled springtime we live in now. Then the long, dark autumn of black holes, and whatever final winter may follow. Our instinct might be to mourn, to see the future eras as a tragedy. But that's a human lens. It's colored by our love for the conditions that birthed us. From the universe's perspective, each chapter is just what comes next. The stelliferous era isn't better than the black hole era. It's different. It's a phase of immense creative energy. Gravity gathers dust into stars. Stars forge the elements for planets and life. It's dynamic, luminous, full of complex change. The black hole era is a phase of deep stillness, of patient dissolution. Gravity's final acts play out in slow motion. Quantum whispers become the dominant sound. One isn't superior to the other. They're sequential, expressions of the same physical laws unfolding across time. This invites a deep appreciation for our current moment. We are living in the cosmic spring. We exist in that narrow sliver of time when the universe is lit. When galaxies spin, when nebulae paint the dark with color, when matter has organized itself into beings that can look up and wonder, all of human civilization, from the first cities to spaceflight, is less than a heartbeat in the life of a single star. And that star's entire life is just a blink in the long gaze of a supermassive black hole. Our moment is fleeting on every scale, but that fleeting nature is what makes it precious. So instead of seeking eternal monuments in the stars, we can learn to value the process, the dynamic process itself. The beauty isn't in something lasting forever. It's in the brilliant, temporary flowering of complexity. A supernova is beautiful not because it creates something permanent, but because it's a spectacular event. A transformative event. A living planet is a miracle not because it will exist for all time, but because for a while chemistry becomes poetry. Our own consciousness, our art, our science, these are rare sparks. Temporary sparks in the cosmic dark. They are the universe for a brief moment, understanding a fragment of its own story. So the lesson of cosmic impermanence isn't despair. It's a lesson in focus. It tells us to pay attention to the chapter we are in, to cherish the light while it shines, to pursue understanding not because it will grant us immortality, but because the act of seeking is the highest expression of this phase. This temporary, luminous phase, we are not just passive observers of a universe winding down. We are participants in its most creative epoch, its most energetic epoch. Our very ability to contemplate the distant, dark future, that's a gift of this golden age of light. It means that for a little while, the cosmos has eyes to see itself, and a mind to ponder its own magnificent, unfolding story. That long, dark future ahead, it makes you reconsider the whole search for other minds, because if a civilization can outlast its star, then its priorities, its technology, none of it would look like ours. We listen for radio signals, a technology we've had for what, a century, but a species thinking in terms of trillions of years wouldn't use something so fleeting. Their communication, their whole way of being would be adapted to the era of black holes. So what would they value? Not rapid expansion, but sustainability. Deep sustainability, not broadcasting for a few centuries but leaving markers designed to last across cosmic epochs. Their greatest project might not be a Dyson sphere around a star. It might be a quantum computer orbiting a black hole, using that immense gravity as a stable foundation for processing, or they might learn to extract the faint Hawking radiation, turning the last energy source in the universe into a slow, steady trickle. Their artifacts wouldn't be metal satellites, they'd rust. They might be carved into space-time itself, using gravitational waves as a permanent record, or placing information in the stable orbits of neutron stars. And some theories go further. A society that advanced might not choose to stay here at all. If black holes are gateways, or if creating new cosmic bubbles is possible, then migration becomes the ultimate adaptation. They wouldn't wait for the freeze. They'd become gardeners, cosmic gardeners, planting new realities, which expands what we should be looking for. Instead of just a message that says hello, we should look for fingerprints. The fingerprints of immense, patient engineering, unexplained structures harvesting energy from strange places, anomalies in the orbits of dead stars. Anomalies that suggest manipulation over eons, or even a deliberate pattern. A galaxy-spanning pattern set up not for us, but for any intelligence that arises across the entire lifespan of the cosmos. So the silence we hear today, that silence isn't necessarily emptiness. It might be a sign that everyone who made it through their technological adolescence has already graduated, moved on to a different kind of existence, one built for the long night ahead. The mind itself is the unknown. Consciousness faces its own test. Could it persist into that deep future? Or is it tied only to the bright springtime of stars? This question sits at the intersection of physics and philosophy. It asks if consciousness is just a local phenomenon, a temporary byproduct of the energetic conditions of our era, or if it could be something more adaptable, a property that could, in some form, endure. Imagine a civilization that has transcended biology. Its members might not live in bodies. They could exist as uploaded patterns, minds running on vast, slow computers. But in the black hole era, even those computers need power. The only reliable source left is Hawking radiation. That faint quantum whisper. Could a society harvest that trickle? To run their collective consciousness on it, thought by slow thought, the processing speed would be glacial. A single calculation might take centuries. Their experience of time would be utterly different. A millennium of our forecast might feel like a single, drawn-out moment. Their entire culture would be one of immense patience. Their art and science unfolding over durations that make geological ages seem quick. But there's a deeper limit. Consciousness, as we understand it, seems to require a flow of information, a processing of differences. It needs a system not in perfect equilibrium. It needs a thermodynamic gradient, however small, to power its computations. In the final stages, as black holes fade and the cosmos approaches heat death, those gradients vanish. The temperature becomes uniform everywhere. When no energy difference exists, can any form of computation continue? Any form of experience? This suggests a possible boundary, a point when the universe becomes not just uninhabited, but fundamentally incapable of hosting any aware observation. The lights go out, and then, much later, the very possibility of a mind to notice the darkness also winks out. Yet, this is where speculation meets mystery. Our understanding of consciousness is primitive. We don't know if it is strictly bound to the information processing we do with brains and silicon. Could there be forms of awareness woven into the fabric of space-time itself? Or into the quantum fields that permeate the void? These are not scientific questions yet, but philosophical ones. They probe whether sentience is a contingent accident or a deeper potential of reality. For now, the conditions that gave rise to us are temporary. the rich chemistry, the abundant energy flows of the stelliferous era. They are the fertile ground from which our kind of questioning mind springs. The long dark era that follows will be, by every measure we have, profoundly inhospitable to anything resembling our form of life or thought. But to declare it absolutely devoid of any possible experience would be to assume we already understand all the forms experience can take. And the history of the cosmos suggests it is always more inventive than we are. So while the physics points toward an end to observers, the ultimate mystery of consciousness leaves a door, however faintly, ajar. It allows for the possibility that in some form, against all odds, the universe might never be entirely alone with its own silence. The universe has this architecture. It's not random, it's a story with a clear, logical progression. Each chapter flows from the one before, driven by physics. The deaths of stars set the stage for the long rule of black holes. And their eventual evaporation paves the way for a final, silent equilibrium. It's a single narrative, a narrative written in gravity, thermodynamics, and quantum mechanics. That narrative gives us a cosmic context. It places our moment within an epic timeline. For nearly all of the universe's future, the sky will be dark. The dominant objects will be gravitational tombs, not luminous furnaces. Our sun, our galaxy, this entire era of stars is a brief anomaly, a cosmic spring that blooms and then fades. Giving way to a much longer autumn and winter, this perspective is humbling. It shrinks human history to less than a blink, but it also elevates our current moment. We are here during the creative peak. We exist in the one chapter where the universe is generous with its light and complexity. This reframes our search for meaning. If the cosmos is headed for an inevitable freeze, then purpose isn't something we find written in the stars. It's something we create within our temporary pocket of order. Our art, our science, our compassion, these are not footnotes. They are the plan. They represent the universe for a brief moment becoming self-aware. Seeking to understand its own story, the vision of the far future doesn't render our present meaningless. It sharpens its focus. It asks us to value the light while it shines, to cherish the connections we make, to pursue knowledge not for eternal glory, but for the privilege of bearing witness. We are the universe's way of knowing itself during its most dynamic age. And that is a responsibility and a gift of staggering beauty. This future isn't a prophecy of emptiness. It's a testament to a grand, structured narrative. A story written in the patient language of physical law. We've traced it from the last starlight to the final whisper of an evaporating black hole. The cosmos moves through distinct chapters. Each phase has its own character, its own beauty. The brilliant, creative fury of stars gives way to gravity's purest expressions, a profound, silent sovereignty. To understand this arc is to grasp a new scale. It redefines words like permanent, it redefines ancient, and it reveals our present moment, this age of light and life, as a singular, fleeting gift. A cosmic springtime. Every question we ask becomes part of the universe's brief opportunity to know itself. This vision of a dark, distant era shouldn't diminish our world. It should illuminate it. It asks us to cherish the vibrant, temporary complexity around us right now, the warmth of a star, the chemistry of a living planet. The spark of a conscious thought. These aren't small things against an infinite dark. They're rare and magnificent events in the grand story. So let this knowledge settle not as a cold forecast, but as a source of profound wonder. We are here now in the luminous chapter. We get to be the part of the cosmos that looks up, that connects the dots, that feels awe at the sheer scope of the tale. That is a privilege of breathtaking depth.